Transformers are essential electrical devices that facilitate the transfer of electrical energy between different circuits through electromagnetic induction. They play a vital role in electrical power distribution systems by enabling the efficient transmission of electricity over long distances. The importance of transformers in electrical systems is significant for several reasons. 1. Efficient power transmission. Transformers allow for the stepping up or stepping down of voltage levels, which is crucial for transmitting electricity efficiently over varying distances. This helps reduce energy losses during transmission. 2. Voltage regulation. Transformers ensure that electronic devices receive the appropriate voltage levels required for their operation. By adjusting voltage levels, transformers help in maintaining the stability and safety of electrical systems. 3. Safety and efficiency. Transformers contribute to the safe and efficient operation of electrical devices by providing the correct voltage levels and isolating circuits when necessary. This helps prevent electrical malfunctions and ensures the longevity of electronic equipment. In summary, transformers are indispensable components in electrical systems, enabling the effective distribution of electricity while ensuring the safety and optimal performance of electronic devices. A transformer is a static electrical device that facilitates the transfer of electrical energy between two or more circuits through the process of electromagnetic induction. It comprises two or more windings, namely the primary and secondary windings, which are wound around a magnetic core. This configuration enables the efficient transfer of energy from one circuit to another. Transformers are primarily utilized to alter the voltage levels within an electrical system. They can either step up or step down the voltage, depending on the specific requirements of the application. By adjusting voltage levels, transformers play a crucial role in ensuring the proper functioning of electrical equipment and systems. The operation of a transformer is based on the principles of electromagnetic induction, particularly Faraday's law of induction and mutual induction. 1. Electromagnetic induction. Faraday's law of induction. This law states that a change in magnetic flux through a circuit induces an electromotive force in the circuit. When an alternating current flows through the primary winding of a transformer, it generates a time-varying magnetic field around it. 2. Mutual induction. Definition. Mutual induction is the process by which a changing magnetic field in the primary winding induces a voltage in the secondary winding. The magnetic field produced by the primary winding passes through the core and intersects with the secondary winding. According to Faraday's law, this changing magnetic field induces a voltage in the secondary winding. Relationship between windings. The voltage induced in the secondary winding is directly proportional to the number of turns in the windings. This relationship is mathematically represented by the transformer equation. Frac V's Vp equals frac n underscore S n underscore P. Where and are the voltages in the secondary and primary windings, while and represent the number of turns in the secondary and primary windings, respectively. Through these principles, transformers efficiently transfer electrical energy between circuits by leveraging the phenomena of electromagnetic and mutual induction. Components of a transformer. Primary and secondary windings. Primary windings. This coil is connected to the input voltage source and generates a magnetic field when an AC voltage is applied. Secondary windings. Connected to the output load, the induced voltage in the secondary winding is delivered to the load for utilization. Winding material. Typically constructed from copper or aluminum due to their excellent electrical conductivity properties. Turns ratio. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines whether the transformer steps up or steps down the voltage. Magnetic core. Function. The magnetic core provides a low reluctance path for the magnetic flux, enabling efficient energy transfer between the windings. Material. Laminated silicon steel is commonly used for the core to reduce eddy current losses and enhance overall efficiency. Core types. Different core types, such as laminated cores, toroidal cores, and ferrite cores, are utilized based on specific application requirements related to efficiency, size, and frequency. Insulation materials. Purpose. Insulation materials prevent electrical short circuits between windings and the core, ensuring the safe and reliable operation of the transformer. Types. Common insulation materials include insulating varnish, paper, and oil. In high-voltage transformers, oil-immersed insulation is often employed for both cooling and insulation purposes. Thermal considerations. Insulation materials must withstand the thermal conditions generated during the transformer's operation to guarantee longevity and reliability in its performance. Types of transformers. Step-up transformer. Function. Increases voltage from the primary winding to the secondary winding. How it works. The number of turns in the secondary winding exceeds the number of turns in the primary winding. Equation and applications. Utilized in power plants to elevate voltage levels for efficient long-distance power transmission. Essential for applications requiring higher voltage levels such as in industrial machinery. Step-down transformer. Function. Decreases voltage from the primary winding to the secondary winding. How it works. The number of turns in the secondary winding is fewer than in the primary winding. Equation and applications. Found in distribution networks to lower high transmission voltages to safer levels for residential and commercial use. Commonly integrated into electronic devices and appliances needing lower operating voltages. Isolation transformer. Purpose. Provides electrical isolation between primary and secondary windings without significant voltage level changes. How it works? Typically, the number of turns in the primary and secondary windings is equivalent. Benefits. Enhances safety by isolating users from direct contact with high-voltage circuits. Reduces electrical noise and interference in sensitive equipment. Applications. Used in medical equipment, computers, and laboratory instruments where isolation is critical for safety and performance. Autotransformer. Unique features. Shares common windings between primary and secondary circuits, offering a compact and efficient design. How it works. A single winding serves as both the primary and secondary winding, with taps at various points to provide different voltage levels. Equation. Where and denote the shared and tapped terms, uses, voltage regulation in power systems. Starting motors in industrial applications. Adjusting voltage levels in specific lighting and audio equipment. Each type of transformer serves distinct functions and finds applications tailored to their unique characteristics, ensuring efficient, safe, and reliable operation within diverse electrical systems. Working principle of transformers. Faraday's law of induction. Basic theory behind transformers. Faraday's law of induction states that a change in magnetic flux through a coil induces an electromotive force in the coil. Formula. Represents the induced EMF. Denotes the number of turns in the coil. Signifies the magnetic flux. Application in transformers. When an alternating current flows through the primary winding, it generates a varying magnetic flux in the core, inducing a voltage in the secondary winding. Construction details. Core types. Laminated core, comprised of stacked layers of silicon steel to reduce eddy current losses, commonly used for its efficiency and cost-effectiveness. Toroidal core, donut-shaped core offering high efficiency and low electromagnetic interference, suitable for precision applications like audio equipment. Ferrite core, constructed from ceramic compounds with magnetic properties, ideal for high-frequency transformers due to low eddy current losses. Core design. Purpose. The core serves as a path for magnetic flux and minimizes losses. Materials. Typically made from high permeability materials to ensure efficient magnetic flux transfer and reduce losses. Operation details. Voltage transformation. Primary to secondary voltage. The induced voltage in the secondary winding is determined by the turns ratio between the primary and secondary windings. Turns ratio equation. Denotes the secondary voltage, represents the primary voltage. Signifies the number of turns in the secondary winding. Denotes the number of turns in the primary winding. Energy transfer. Magnetic flux. UC in the primary winding generates magnetic flux in the core, inducing a voltage in the secondary winding. Efficiency considerations. Transformers exhibit high efficiency, typically ranging from 95% to 99%, with losses primarily from core losses and copper losses. Example. For a transformer with 100 turns in the primary winding, 200 turns in the secondary winding, and an input voltage of 120 volts, the output voltage will be. These operational principles and construction details ensure transformers function effectively, enabling the transfer of electrical energy across different voltage levels while minimizing energy losses. The applications of transformers span across various sectors, including power distribution. Transformers play a crucial role in electrical grids, facilitating efficient energy transmission. Electronic devices. Transformers are utilized in a wide range of gadgets and appliances to ensure proper voltage and current supply. Industrial applications. Transformers are essential for powering heavy machinery and industrial equipment in various industrial settings. In transformer design and efficiency, key aspects include core materials and design. The choice of core materials and design significantly affects the efficiency of transformers. Winding configurations. Different winding setups, such as layer winding, helical winding, and disc winding, have implications for performance and cooling. Losses in transformers. Understanding core loss, copper loss, and implementing methods to reduce these losses are critical for enhancing transformer efficiency. In maintenance and safety practices for transformers, routine maintenance involves key practices such as regular inspections, testing, and cleaning to ensure optimal performance. Safety precautions. Important measures include ensuring isolation before maintenance, using protective equipment, and providing proper training for personnel. Troubleshooting common issues. Addressing common problems like overheating, noise, and voltage irregularities through appropriate solutions and testing procedures. Innovations and future trends in transformer technology include smart transformers, advancements in smart grid technology, featuring real-time monitoring, automatic fault detection, and remote control for improved reliability and efficiency. Eco-friendly transformers, development of environmentally friendly materials and designs, such as biodegradable insulation and energy-efficient designs to reduce environmental impact. Future trends. Emerging trends and future prospects in transformer technology, including solid-state transformers, integration with renewable energy sources, and enhanced monitoring and control using IoT and AI for smarter transformer management. In conclusion, transformers are indispensable components in electrical systems, facilitating the efficient transfer of electrical energy across different circuits. Their diverse applications in power distribution, electronic devices, and industrial settings underscore their pivotal role in ensuring reliable energy transmission. Understanding transformer design, efficiency considerations, maintenance practices, safety precautions, and future trends is essential for optimizing their performance and enhancing energy efficiency. The continuous advancements in transformer technology, such as smart transformers and eco-friendly designs, reflect the ongoing evolution towards a more sustainable and efficient energy infrastructure. Transformers remain vital in modern society, driving innovation, reliability, and sustainability in the electrical power sector.